All right, so I've got 3 videos here I'm going to do for you about what we call thin film interference. Okay, so when you think about the word film here, you need to think like this picture here. Okay, it's wet asphalt, but there's a thin film of oil or gasoline or something on top of it. Okay, and so when we talk about thin film, we're talking about a layer of something that's really thin. And usually by thin, we mean just a few wavelengths of light thick. Okay, and a wavelength of light's pretty darn short. So these are really, really thin materials. Okay, and so we'll talk about path differences, to get us started, and then we're going to move into to what happens when you've got something very thin that light can go through. Okay, so talking about path differences here. Now we've talked about this a little bit before. All right, so if we have a speaker behind a speaker, and somehow magically we could make all the sound stay in like a beam or something like that. And okay, so then these 2 beams of sound overlap. All right, so the 2 sources of sound, there's going to be some interference. Okay, and we talked about how there's extremes on the one end. The 2 sources of sound could have constructive interference, which creates twice as much stuff, or they could have destructive interference, which basically is going to produce nothing. Okay, but in between, there's a whole range of things. Okay, so again, constructive and destructive are special cases of our interference. All right, so what makes the difference is what we call the path difference from here to here. All right, so we've got these 2 sources of sound, and if I'm over here, all right, maybe let's say it's 1.2 meters there. Well, here out to the same location in space, it's going to be 1.2 plus delta x. Okay, now during the 1.2 part, both waves are going to be doing the same sorts of thing. All right, so the only difference in the 2 waves is how they got started. Okay, is what is the delta x. Okay, now if the path difference turns out to be what we call an integral number of wavelengths, all right, and in fact, I want to call this capital N lambda instead of lowercase. We're going to do the same thing down here. If it's an integral number, so it's a 1 full wavelength, 2 full wavelengths, 17 full wavelengths, then we can get constructive interference because the 2 waves will be synchronized when they come out. Okay, they'll be exactly in sync. On the other hand, if that path difference is like 2.5 or 17.5 wavelengths, then that means by the time the second one gets to the start of the first one, it's moving the wrong direction. Okay, and so they're going to end up doing one of these sorts of things. I'm off campus. One of these sorts of things, and they will flatline. Okay, they're not going to result in anything. Okay, so constructive and destructive depends on that path difference. So kind of keep that in mind as we move forward here. All right. So now let's take a quick look and remind ourselves what happens whenever you have a boundary. Okay, and remember, boundary is defined by a difference in impedance, and usually that means the wave is going to speed up or slow down. Something about the transmissibility of the wave is different. Okay, so we could have one case where the wave hits a boundary, and then across that boundary it has to go slower. Okay, and that's going to scrunch our wavelength. Or we could have the other situation where once it crosses a boundary, it's got to go faster, and then that's going to lengthen that wave, the wavelength there. Okay, all right, now at every boundary you're going to get some transmission and some reflection. All right. And they kind of work out to be, something like maybe 90% and 10%. Okay. So in that case, it would be kind of hard. If this was light, it would be hard to see that reflection. All right. It wouldn't show up very well. Okay. But you might have some other situation where, for whatever reason, not very much light gets through and most of the light pops out on the other side. So here's where you'd have a really strong reflection like this. Okay. So if we think about, maybe a mirror, the mirror's got, you've got air and then you've got glass and then there's some silver backing on it. Okay. On this silver backing, you're not going to have any transmission. So it's all going to be reflected. But from the glass, between the air and the glass, there's a tiny bit of reflection there. Okay. So sometimes when you look in a mirror, you can see the two reflections, but the second reflection is much stronger than the first reflection. Okay. Alrighty. So, but what happens if we've got a sandwich? All right. So we got 3 layers. All right. We've got the layer where it's coming in. Then we've got a thin little layer. That's our thin film. And then there's another space. Okay. So this could be sort of like, imagine a soap bubble. All right. So we might have air over here, air on the inside of the balloon, and then the soap film is right here. Okay, just like that. And the way the light moves through the soap film and through the air is different. Okay. Now, notice I've got a boundary here. So there's going to be transmission. So we've got here, transmission, but also reflection. Okay. However, there's another boundary over here. Okay. And the boundary on that side doesn't know anything about the first boundary. Okay. So it's kind of like we have to kind of restart, and we're actually going to get another reflection here. Okay. And some of that is going to get through on this side over here. Now, there will be a little bit of reflection off of that, and it'll go back the other way. Hit the second boundary, reflect, come back, hit the first boundary, reflect. Okay, so you've got some light that's going to kind of be like, kind of like stuck inside there. Okay, and gradually get weaker and weaker and weaker. Okay. So this thing can get kind of complicated. And if you have to, you can treat it as a limit problem, like from Calc 2 with an infinite series. So we could have an infinite number of reflections. We want to say, so what happens as we begin to have an infinite number of reflections? Okay, that sort of thing. And we're going to be looking at a couple of special cases where those infinite number of reflections aren't really going to come into play. So this first bounce off the second boundary. Okay, so the second boundary is this one. That's the most important stuff. Okay, now, having said all that, let me get rid of what I just scribbled all over there. Okay, we can kind of imagine at the first boundary that you've got a little, speaker. And it's sending out this wave that we see here. But what if on the other side of that, we had a speaker, all right, and it's producing this, and it goes all the way over, bounces, and then comes back. Okay, so that we have this right here as our path difference. Okay, so remember, path difference, that's when we were like talking about a speaker here, a speaker back here, and the difference between those two. All right, that's our path difference. All right, so in this case, then the path difference is all the way across the film and all the way back. All right, to pop out all the way across and all the way back. And so what happens across this difference becomes really important. Okay, so does this turn out to be kind of an n lambda thing, where we're going to get constructive interference? Or does it turn out to be kind of an n plus a half lambda thing where we're going to get destructive interference. All right. So that's what we're going to be looking at. So here are those two special cases. All right. So in the top case, the light punches through here, bounces, and then punches back through on this side. And the way it punches through this transmission off of the front face is exactly out of phase with the reflection off the front face. And they're going to cancel each other out. Okay, so we get destructive interference on the outside of this thing. Okay, destructive interference on the outside. Now, let's compare that to the other one. Okay, now the light goes over and it comes back, and it's not as far. It's a little bit thinner. Okay, and so we've got the light that reflects off the first boundary and the light that's transmitted through the first boundary this way. Now they're in phase. Okay, so they're going to interfere with each other in a constructive way. Okay, so here's our two ends. All right, constructive and destructive. So you can kind of imagine in between these two cases. So we've got a certain thickness of our film, and maybe we get destructive. But if we could gradually make this thing get thinner, all right, we wouldn't have destructive anymore. It'd be something in between, but then it would become constructive. And if we kept going, then it wouldn't be constructive anymore. We would reach a point where it would be destructive again. And if we kept going, then it might become constructive again. Sort of like that. Okay, so there's a relationship between the thickness of our film, which we're going to call T. Think T for film. That's not T for time or T for period or all right. There's just, there's only so many letters in the alphabet. At some point you're going to be recycling. So traditionally we use T for the thickness of the film. But there's a relationship between T and the wavelength of the light, lambda, and that's going to tell us whether we get destructive or constructive interference. Okay, now let's look at a couple examples, and then we'll come back. All right, so this is an example. I showed this picture right at the very beginning, okay? But you see the different colors, all right? Now, that relationship between the thickness, I need a new color, between the thickness T and the wavelength lambda, all right, because there's a relationship there, that means out here I've got a certain wavelength and there must be a certain thickness of that film that causes that yellow looking light to be constructively projected away from the first boundary. Okay, so I've got constructive interference there with that kind of color of yellow. Somewhere else, the thickness is different. And so the constructive interference occurs at a different wavelength. Somewhere else, the thickness is different and constructive interference occurs at a different wavelength. Okay, so these bands of colors really tell us about how thick that film is. Okay, so this film here, the gasoline on top of the water or whatever it is, all right, it's not uniformly thick. It's changing on us, all right? And depending on how thick or thin it is, a different color will experience constructive interference when it pops back out of the front face, okay? Now, this occurs in nature quite a bit, all right? It turns out that in nature, most things that have a color, it's because there's a certain pigment to it, okay? However, there is no blue pigment in nature, okay? But we have things that are blue in nature, all right? Birds, peacocks, people with blue eyes, okay? And there's no blue pigment. Instead, what's happening is there are layers of optics And the way those layers are working, the blue light is constructively transmitted off of that first layer. Okay, and that's what causes people who have blue eyes. That's why their eyes are blue. It's why peacocks have blue, blue jays, whatever, anything, bluebirds, anything blue that occurs in nature. That's why it's happening. It's because you've got this layered structure creating this interference. Okay, so I'm going to stop this here. All right, in the next video, I'll be talking. We're going to get into the mathematics, and we're going to figure out what exactly is that relationship between the thickness and the wavelength, so that we could know if we're going to get constructive or destructive or something in between. Okay, so that's next.